This is an automated code generator producing flight control source code. In high-density aerospace programs, this volume of code is generated at a scale that makes line-by-line human review impossible to maintain. Most teams use model-based design, generating this source code automatically from Simulink or SCADE models. Because the generator now creates the software directly from the model, it is no longer a support tool, it is an active link in the production chain. This shift changes the nature of software errors. A generator defect is not a random or transient glitch. If the generator contains a flaw, it injects the same error into every build and every redundant hardware lane. Standard architectural redundancy cannot mitigate this. Because every lane fails identically at the same moment, the safety benefits of hardware voting are effectively neutralized. DO-178C provides a regulatory path to manage this risk. To ensure the safety of the final executable, engineers must either verify the tool's output or qualify the tool itself. It is important to note that tool qualification replaces output verification. It is a substitution for manual review, not a secondary layer of tasks added to the project. There is a common industry assumption that generated code is inherently unreadable or impossible to trace. In reality, generated code can be reviewed by human eyes. Teams choose qualification because reviewing millions of generated lines on every software build is programmatically impractical, not because the code is technically impossible to audit. To determine how much evidence is required for a tool, the standard uses a classification system. This raises a foundational question. How do we scale the rigor of qualification against the actual criticality of the flight software? We start with Criterion 1. This applies when the tool's output becomes part of the airborne software and could therefore insert an error into the system. A code generator is the primary example of a Criterion 1 tool. Criterion 2 applies when a tool automates verification and its output is used to justify eliminating another manual process. An example is a structural coverage analyzer used to drop a manual code review. Criterion 3 applies when a tool automates verification but eliminates nothing from the existing certification process. In short, a tool's criterion is defined by what it physically produces, or which manual engineering steps it allows a team to skip. The required tool qualification level, or TQL, is derived by combining the tool's criterion with the software level of the target aircraft system. This mapping is codified in DO-178C, Table 12.1. Criterion 1 gives TQL1 at level A, TQL2 at B, TQL3 at C, and TQL4 at D. Criterion 2 gives TQL4 at levels A and B, and TQL5 at C and D. Criterion 3 gives TQL5 at every software level. This matrix forces a program to prove the integrity of an automation tool based on the impact a failure could have on the aircraft safety. Assigning a TQL number is only the first step. The real complexity lies in what these ratings demand from the engineering team. TQL5 is the entry-level requirement. It requires basic tool requirements and operational verification to prove the tool works in its target environment. As the TQL number moves toward 1, the evidence requirements escalate significantly. Lower TQL numbers add the need for low-level tool requirements, documented tool architecture, and structural coverage analysis of the tool's own source code. For the most critical systems, the automation tool must be verified with the same level of rigor as the airborne software it generates. The programmatic cost is substantial. Achieving a TQL1 qualification from scratch is a multi-year engineering effort. To manage this, many programs use vendor qualification kits. These kits provide the portion of the evidence owned by the tool developer, such as the tool's internal test results and requirements. However, a kit is not a turnkey solution for certification. The tool user still owns the operational requirements and the operational validation that must be performed within their specific development environment. Ultimately, tool qualification trades the impracticality of manual review for a front-loaded verification of the tool's requirements and structural integrity. This process ensures the source code is correct, which leads us to the next challenge: ensuring the compiler maintains that correctness as it translates source into object code.